Remember back in Chem 200 and 152, the solubility rules? Well, the solubility rules were basically just rules. They tell you that, oh yeah, all nitrate salts, anything with a nitrate anion, are going to be soluble in water up to the solubility limit. Anything that might have chlorides or halogens, but is with lead, mercury, um, mercury, or silver, is not going to be soluble. In reality, they're still soluble, but not to a quantity that is noticeable. Some of it will still dissolve. What we're going to do in this section is actually calculate how much of it dissolves. When something's 100% soluble, how much of it really is soluble based on the mass action expression. When the solubility rule says it's not soluble, we can still calculate how much of it goes into solution. That's what this whole um, chapter section is all about, quantifying how much is dissolved, or how much goes into solution, or how much of the product is produced. Okay, solving equilibrium problems. So what you see here is a guy looking at this reaction, and he's just waiting because, one, it's slow and eventually it'll go, but he wants to know how much product is produced. That's what this chapter is solving. So we're solving equilibrium problems. There are many types of equilibrium problems, okay, depending on the complication, but we can basically distill it down to two types. And the two types are, given the concentrations at equilibrium, solve for the equilibrium constant. So it has to be at equilibrium in order for you to solve for the equilibrium constant. And the second type of question, which is much more complicated, is that if you know the equilibrium constant, because generally those things are generated. People around the world have done that equation reaction, and now they know the equilibrium constant. And so what you need to do is figure out how much product is produced under these set of conditions. It's like stoichiometry again. Remember, in stoichiometry, general chemistry, you're given reactants and you're told to calculate, depending on which one is the limiting agent, how much product is produced. Okay, and then you can also calculate a percent you can calculate a theoretical yield, and then you could also calculate a percent yield. And the percent yield is based on what you actually recovered, given how much you should have recovered if everything was 100% converted. Well, things in general are not 100% conversion. The products are formed and then they back react. So we need to figure out how much products do we get when we run one of these reactions that have equilibrium involved. This is where you guys will learn how to do that. So there's more math here. Okay, so the type one of problem is, first type of problem is just figuring out the equilibrium constant. If you know the chemical concentrations at equilibrium, you just stick it into the mass action expression. Of course, you're not going to put in the liquid or the solid and then calculate the equilibrium constant that way. So these things are pretty straightforward. Okay, step one involved in these types of equations is write the balance equation for the reaction. You need to balance it, because if you don't balance it, you're not going to get the right mass action expression. The other thing you need to do is you also need to note the phase. Note the phase. I should include that in there. 2, write the equilibrium expression called the mass action expression, products over reactant. And then stick the equilibrium concentrations into the mass action expression and calculate the equilibrium constant. We already did that in the previous slides. Okay, here's a problem. We have 5-liter volume, okay, and it's at 1400 degrees. The reason why we always try and cite the temperature is because that equilibrium constant always changes with temperature. So when you cite an equilibrium constant, you have to specify the temperature. Otherwise, it's a way of verifying whether it's right or not. Okay, so you got this reaction. It's in a 5-liter vessel. Generally, when we have a vessel, we have some sort of enclosed container like that. It's enclosed and the reaction is taking place here. We've got carbon monoxide, we've got oxygen in here, and we've got carbon dioxide in here. So that reaction is in equilibrium. It tells you, given the following reaction, CO plus 1/2 oxygen gives you carbon dioxide. Calculate the equilibrium constant Kc and Kp after, and we could calculate Kc and Kp because all of these are in the gas phase. And even if I didn't put the phase in, you guys should be able to establish that these things are in the gas phase, especially since the temperature is very high. And at room temperature, carbon monoxide, carbon dioxide, and oxygen gas are all gas. So at higher temperature, for sure, it's going to be gas. Okay, so you need to use your knowledge of chemistry in some of these problems. Calculate Kc and Kp with when the equilibrium is achieved. Okay, now I realize that some of you have difficulty solving word problems, so you got to break it down. You got to take a look at each word and try and translate it in a way so that it's clear in your mind what's going on. So we're establishing equilibrium, and this right here is what we call an ice table. Ice meaning not your international correction people that goes in and get immigrants. ICE just means that it's the initial, the change, and the equilibrium conditions for equilibrium. Okay, that's what the ICE means. And some people might call this the rice table, where you have the reaction, the initial, the change, and the equilibrium condition. ICE or rice, you need to get that when you're solving equilibrium problems. Okay. Now, the key here is that you've got 4.95 moles of CO2. You've got 0.050 moles of CO, and you've got 0.0250 moles of oxygen. You can't just use that because those are moles, not molarity. So you need to divide by 5 liters. You need to divide by 5 liters. And that'll get you your molar concentration. Once you have your molar concentration, then you can put in your mass action expression, K, and in this particular case, we have moles per volume. So that's molarity. So that's Kc is equal to products, CO2, divided by reactant, CO, and oxygen to the 1/2. Why 1/2? Look at that. That's where the 1/2 comes from. Okay. So what we need to do is we need to convert all of these. Rice means reaction, initial, change, and equilibrium. So what you guys are going to be doing when we get this ice table or rice table is you guys are going to establish what are the concentrations in the initial, what are the concentrations when they change, and what are the concentrations at equilibrium. So right now we only have the concentrations at equilibrium. That's what this is. We don't have to worry about that because it's not important for this problem. In order to get the equilibrium constant, you need the concentrations at equilibrium. And the problem tells you it's at equilibrium. Equilibrium is achieved, has been achieved. So you got to read what the problem gives you, because if it didn't give you that, then there was more work. But now we do have the concentrations at equilibrium, and this is basically what it looks like. When you take 0.05 and you divide it by 5, because that's the volume, you get 1 times 10 to the minus 2. When you take 0.025 and divide it by 5, you get 5 times 10 to the minus 3. When you take 4.95 and divide it by 5, you get 9.9 times 10 to the minus 1. You stick that into the mass action expression, you get this value. 1.4 times 10 to the third. Look at that value. That's basically 1,400. That's a big number, fairly big number. that means that the reaction is mostly favoring the product. This reaction will convert over to product just because K equilibrium is somewhat of a big number. What is Kp? Kp is going to, remember this relationship, Kp equals Kc RT delta N, positive delta N. If you didn't remember, it's positive. The way I remember that is that when this is P, it means positive, and that's what that is right there. That's how I remember it. Otherwise, you get your positive and negative backwards. Or you can look it up. Exams before your final is, in your final, you're going to be given an equation. You might be even given this equation, but they're open book, open notes, not open friends. Okay, so you can just write this in your a sheet of equations, or you can use the equation sheet that I referred to earlier. It's in there. Anyway, what is Kp? Well, Kp equals Kc, 1.40 times 10 to the third. And what is RT? RT, and what is delta N? Well, delta N is, this is 1, and this is minus 1.5. So delta N equals minus 0.5. So we need to minus 0.5. Minus 1/2 is the square root. So this is Kp equals 1.40 times 10 to the minus 3. The negative here tells you it's the reciprocal, and the 0.5 tells you it's the square root of RT. So the negative tells you it's in the denominator. The 1/2, 0.5, tells you it's a square root. So
Perfect.
what we need to, yes.
Could you just walk over where you got delta N,
Yeah,
how you added the two figures
CO2,
together?
there's one right here, one right here. So that's that. Delta N equals, and then the product is oxygen.
Coefficients of each?
Yes,
Okay.
exactly. That's exactly it. So it's 1 minus 1/2 and plus 1. So that's your product, and that's your reactant. So 1 minus 1.5 equals negative 0.5. Is that clear?
Yes, and you have the products on the right, the reactants are,
Yes, exactly.
okay.
Exactly. And they're all gases. So you don't have to worry about neglecting any. Okay. So that's a good question because that's critical for this problem. So once you have that, then you take 1.4 times 10 to the minus 3. Delta N is 0.5, so that's the square root. And the negative, why the negative? Because it's a negative 0.5. And it's a positive in this equation. Okay, it's a positive here. If it was a negative and a negative would make it a positive. But in this particular case, that equation is positive delta N. Delta N is negative 5. So that's what we have right here, negative 0.5. So let me just show you that real quick. Let me clear this and show you that relationship. That's that relationship right there. And what we see is that Kp is 1.2 times 10, 1.2 times 10 to the second, okay, 10 to the 2. So this is nothing more than 120, whereas this is a 1,400. We're sticking with two significant figures, but that's going to be, that's your Kp, and that's your Kc value. The problem in itself is not difficult. It's just making sure you use the right one. And again, where you're going to make mistake is not using the right problem, not calculating delta N. Maybe you're calculating delta N, but you're including the solids, the aqueous, and not sticking to just the gas. Those are all problematic areas that I see time and again when you guys do problems. It's only the gas phase, because remember, delta N comes from PV equals nRT, and only chemicals in the gas phase will obey PV equals nRT. If it's a liquid, if it's a solid, it doesn't, you don't have PV equals nRT established. We're assuming ideal gases, okay? This is the second question, and I'll start here next time. You guys take a look at this. This right here tells you that you have concentrations of carbon dioxide, hydrogen, and water in a 1 liter. So that's your starting concentration. And then it tells you at equilibrium, your concentration of carbon dioxide is 0.094. So again, let me show you the ICE table. First, write your balanced chemical equation. All these are gases. Okay, carbon dioxide is a gas, hydrogen is a gas, CO is a gas, water is a gas. Double check that the equation is balanced. So you've got two hydrogens on both sides, you've got one carbon on both sides, and you've got two oxygens both sides. It's a balance. It's a 1 to 1 to 1 to 1 ratio. The initial is right here because they tell you if a mixture of, when they tell you it's a mixture of, and that's hard to sort of grasp, that's your starting point. That's what you have when you're given this reaction. So you put that in the initial line, 0.10 molar CO2, 0.05 moles, not molar, moles of hydrogen, and 0.10 moles of water. And they don't mention carbon monoxide. If they don't mention it, assume it's zero, okay? You need to make assumption. The hard part about this part of the this course is you got to make a lot of assumptions, but you got to make sure that assumption is valid. One of the assumptions here is that it doesn't mention CO, so it was never introduced in the beginning. You assume it's zero. Then you allow that reaction to take place. What happens in this delta line is that for every one carbon dioxide, you also consume one hydrogen. That's why I have a minus X here and a minus X, because they react in a 1-to-1 ratio. But they produce carbon monoxide and water in a 1-to-1 ratio as well. So use a variable, because when one decreases, the other one has to increase in the same quantity as the stoichiometry. That's the key. If there was 2 here, then you would put positive 2x. Okay? So that's the key to the balance equation. Use the balance equation to establish the relationship of each. Now, it just so happens that in this particular problem, okay, you have this information right here. They tell you that at equilibrium, your carbon dioxide is 0.094 molar, but you don't know the others. So if you try to put this into your mass action expression, this quantity, it's going to be difficult. What you need to do is you need to figure out where's another equation I can use that will give me the X value, because if you don't know X, then you don't know the equilibrium concentration. That's how you get the equilibrium concentration, is figure out how much you have in the beginning and remove that is going to be converted over to product, or add that which is being converted to product. That's why we have minus X here, because reactants are being consumed and products are being formed as reaction goes from left to right. Now, if the reaction is going from right to left, if it's reversing, just stick with these signs and your answer will become a negative value. And the negative just tells you that it's moving in the reverse direction. Anyway, the key in this particular problem, and I'll finish, I'll stop after this, is that we know that your equilibrium is equal to, equilibrium concentration is equal to the initial minus the change. Our initial is 0.100, our change is minus X, but our equilibrium is 0.0954. So we can solve for X in this problem. We can solve for X, and that X value is going to be in the, you can see that right here, it's 0.0046. That X is the same for this, and for that, because they all are related based on the stoichiometry. So once we know what X is, then we can carry out the math. 0.1000 minus plus, 0.0046, and that'll be the equilibrium concentration for that. This will just be 0.0046 because we started with 0. This is 0.0500 minus 0.0046. So now you see that we can get the equilibrium concentrations. And when we do that, let me clear this. This is basically the concentrations. This will be that value, this value, that value. We can now calculate Kc. And what's delta N for this problem? This is 1, this is 1, this is 1, this is 1. 2 minus 2 is 0. Anything to the 0 power is equal to 1. Okay, RT to the 0, anything. 1 billion to the 0 is 1. Negative 3.87 to the 0 power is 1, positive 1. Anything to the 0 power is just 1. So um, Kc and Kp are equal to each other. Why? Because RT to the 0 goes to 1. So next time, what I will do is I'll go into the more challenging problems. You think this was difficult? Well, this is fairly easy. But at least it establishes you from this point on how to think in terms of how to solve these problems. You need that rice table or ice table in order to account how the chemicals are changing over time. The key here is that you need to figure out what the concentrations are at equilibrium, because that's the how much product is produced when this reaction looks like it stopped. These are your answers right here, the concentrations at equilibrium. So I think we left off here last time. We talked about how to solve equilibrium problems. Remember I told you there were two types. One is where you're given conditions, and remember you need to get the equilibrium concentrations. If you can get the equilibrium concentrations, then there's a way to calculate the equilibrium constant. So once you get the equilibrium concentrations, then you stick it into the law of mass action, or also known as the mass action expression. You put the products over the reactant and you do the math, and that'll get you the equilibrium constant. Now, we don't really worry about the units of the equilibrium constant because depending on the complexity of the reaction, the units are going to vary. So we just leave it out, okay? Um, Unlike kinetics, where you actually have to carry the units. But in this particular case, we leave the units out just because if you solve the problem correctly, you'll get the correct equilibrium constant. Um, so I think we left off with this problem last time. And the key to this particular problem was, if you just look at this problem right here and try to put these variables, because this right here is nothing more than 0.100 minus x. This is x, and this is 0.500. This is plus x, I mean. This is 0.0500 minus x. If you put that in a mass action expression, then you couldn't solve it because your x values are all over the place. But if you concentrate on one particular area where you can say that 0.100 minus x equals 0.054, then you can solve for x. And remember that x is the quantity that relates each of the species to each other, and they're related through the balance equation. So once you get the x value, then you can calculate all these quantities here and then stick it into the mass action expression and solve for K equilibrium. Now let's take a look at a more complex. And the other thing I want you to note here is that if you look at the balance equation, this is a 1, this is a 1. So the sum of the coefficient of the products equals 2. This is a 1, this is a 1. The sum of the coefficient of the reactant equals 2. 2 minus 2 equals 0. So delta N equals 0. So RT to the 0 power is just 1. So Kc and Kp in this particular case are equal to each other. Okay. So remember that if there are no change in the moles of gas in the balance equation, okay, then the equilibrium constant expressed in molarity is equal to the equilibrium constant expressed in atmospheric pressure. So let's take a look at these problems. These are the problems where you really need to put on your thinking caps. For those of you in lab, take a look at the activity that we're going to do next Wednesday, because you have a bunch of these types of problems, okay? So these are where you're given the initial concentration and probably given the equilibrium constant, and you're trying to figure out what are the concentrations of all species in the reaction mixture at equilibrium. So it's similar to what you guys did in Chem 200, where you have the initial reactant and you're trying to figure out how much product is produced, but it's different because it's not 100% conversion. The efficiency of the reaction is dictated by the equilibrium constant. And you have to use that constant to determine how much product is produced and how much reactant remains. Okay, so let's take a look at the strategy you use in order to solve these problems. Always start with the balance equation. Make note of the phases of the chemical and then look at the conditions of the reaction. So generally, like I said, you're given the initial concentration and you're generally given the equilibrium constant. Balance the equation, make note of the solid, the liquid, aqueous, and gas. Write the equilibrium expression. Now, as you do this more, a lot of you are going to skip and just stick it into the mass action expression. And then you're going to probably make a mistake because you're not accounting for how the chemicals behave in a chemical reaction. How many, what the coefficients are. And so if you do that, then you might have the right idea, but you're going to make silly mistakes. Okay. And let me point that out as I go further into this discussion. That way you don't make that same mistake as you solve these types of problems. Um, List the initial conditions. That is, if you're given reactant, write that in the ice table. Okay, the initial um, concentrations. If you're not given concentrations, then convert it to molarity. You need to know how to do that. If you're given pressure, okay, then make sure you use the partial pressure of each chemical. And in general, you use, make sure it's consistent. If you're using atmosphere, make sure it's atmosphere throughout. And generally, if you're using R, PV equals nRT, you better make sure that you are in atmosphere because 8.314 is based on atmospheric pressure. Now, there's a way to use like torr or millimeters of mercury, but that's basically if you're not using the quantity R, and everything will cancel anyway. But again, I just want to give you a heads up on that. The initial conditions, remember that the ice table or the I delta E table or the rice table, many different ways of saying the same thing, uh, gives you a way of accounting how the chemicals behave through the reaction. What chemicals you start with, how much you have, how they break down in the course of the chemical reaction, and then how much chemical you should expect at equilibrium. That's basically what the ice table is for. It's to so that you can account for all the chemicals as the reaction progresses. And you use a quantity X. We use X. You could use any variable if you want. You can use Z or Q or whatever, but it's just like math. X is what you solve for, okay? Later on, if you have multi-variables, you might have X and Y or Q and R. Again, it's just a variable you solve for. So make sure you understand that these quantities, these variables are what you basically put in your math equations. Then plug in what you know and then try and solve for X. And sometimes the mathematics will be complicated. In general, if we have math that involves the third or higher order, we can simplify it. If it's second order, that is, there's a square term in there, then we solve it via quadratic. Okay, so make sure you get a understand how to solve quadratic formulas, or just go to the internet and get a quadratic calculator. Some of you might have a quadratic formula calculator already. Well, you just need to make sure that you express the equation in terms of ax squared plus bx plus c equals 0. That way you can use the term a, b, and c to solve into the quadratic calculator. So those are the essential ingredients that you guys will need. And then once you have that, you have X. Sometimes X isn't the answer. It might be asking you, what is the percent yield? So what you need to do, of course, is look for other information. Or it might ask you how much reactant is remains, or maybe the product is 2x. So you need to multiply 2 by that x term. So read the question and make sure you answer the question completely. Don't stop with X. In most cases, X might be the answer, but maybe you need to do something else to get the right answer. And in the multiple choice exam, they'll try and trick you to make sure that you understand that you're not just solving for X, you're actually solving for whatever the question is asking for. Okay, so please read the question entirely and don't make false assumption. Don't just say, oh yeah, here's X, then move on to the next one. Read the question, make sure you know what the question is asking, and at the end, make sure you are addressing the question. So this is basically the guidelines of solving equilibrium problems. So let's take a look at an example. Here we have sulfur trioxide, and it tells you how much SO3 is formed. Now you got to make sure that you know how to read word problems. And I know some of you get confused in the vocabulary, but when it says form, you know it's a product. Okay, so you know SO3 is a product. How much SO3 is formed when SO2 and NO2 are in 1 liter at 821? So your starting um, reactants here are SO2 and NO2 to produce SO3. And of course, in this particular case, you're going to need another reaction here, because what happens is that this is not a balanced equation. Probably the other is going to be either nitrogen gas or NO. Anyway, the answer here is NO. And you could have seen that because one of the oxygens transfers to SO2, and then you get NO remaining. So this is just part of the, oops, this is just part of what you
Uh-oh.
guys should know when you, from chemistry 200, okay?
Professor,
The product, yes.
quick question about delta N. We only include the reactants and products for calculating it when they're in the gas phase, correct?
When you're converting Kc or when you're relating Kc and Kp. If you're given a molar concentration, your best way to get the equilibrium constant is just go after Kc. Of course, if you're given the molar concentration, you can convert all those molar concentration to partial pressure by PV equals nRT, and then you can calculate um, Kp directly. But if you're given Kc, you need to get delta N to calculate Kp. And in this case, you can see it's a 1 to 1 to 1 ratio. Kc and Kp are equal. Okay. But yeah, delta N is when you're relating the equilibrium constant that is expressed in molarity to the equilibrium constant when it's expressed in partial pressure. That's the time you need delta N. Okay. And in this case, it's not even necessary because this is a 1 to 1 to 1 ratio. They're all in the gas phase. But yeah, thanks for asking. That's always important when you solve problems like these. So here's the initial. They tell you that you have zero point 0.5 and zero point 0.5. So that's the initial. They don't tell you any product has formed. So just assume that initially you don't have any SO3 and NO2. You've got to make that assumption right here. Otherwise, you're going to get stuck or you're going to be going into the wrong calculation. Now, here's where you take into account the balance equation. In this balance equation, what you notice is that when SO2 is consumed during the course of the reaction, what you basically have is a reaction vessel here. You charge it with SO2 and NO2, and during the course of the reaction, some of this will break down and you form SO3, and some of this will convert to NO. So in your reaction vessel, you actually have at equilibrium O4, but initially you do not have O4, you only have your initial chemicals. Now, if you look at the balance equation, for every one SO2 that changes, so we may represent that as minus X, one NO2 is also going to be consumed, so we put minus X. The minus tells you they're going to be decreasing. It's going to be vanishing. And you form one SO3 and one NO. That's what's being formed. So again, the plus and the minus is to take into account what is disappearing and what is forming. And here it's pretty straightforward because it's a 1 to 1 to 1 ratio. Okay. So what is the equilibrium concentration? The equilibrium concentration is just initial minus the change, and that's the equilibrium concentration. So the initial is zero point 0.5 minus the change. That's the equilibrium concentration for SO2. The initial minus the change, that's the equilibrium concentration for NO2. Here we have 0 plus X because it's forming now, so it's plus X. And here we have 0 plus X. Okay, we can like take one of these and solve for that 0.50 like we did in the other one, minus X equals 0.50 minus X. If there was a known quantity here, then we could solve for X. This is just the identifying equation. One side is equal to the other side. So there's no way of using the same strategy that we used last time to get X. What we need to do is we need to use the mass action expression. So we do that by putting it products X, that's, well, let me write it this way, okay? SO3 times NO all over reactant. And again, these are to the first power because the coefficient is 1, SO2, NO2 to the first power. But then we can substitute these guys, X times X over 0.50 minus X, 0.50 minus X. And that's equal to, in this particular case, Kc, which is Kp because n, delta n is 1. So if you take a look at this and you're, remember that in math, if you are in calculus or even algebra, you will remember as you solve those math problems that there's generally a simple way to solve things if you recognize the shortcut, and there's a brute force way of solving things. Brute force way will eventually get you there, but it takes some time. If you want to solve this through the brute force way, then this would be x squared, and this would be 0.50 squared minus 0.50 minus 0.50x. Basically, just multiplying these two terms plus x squared. So you have to multiply these two terms out. What you should recognize, however, is that this is a perfect square. You can do this. And when it's a perfect square, the math is so much easier. Why? Because you can take the square root of both sides. Much easier to do that than multiplying the denominator by itself. Then you have to go through the quadratic. So recognize shortcuts like that. And for those of you who are in science, of course, you're doing all kinds of math. And hopefully you recognize that. Because once you do that, then everything becomes clear. Okay? Everything becomes clear. When you take the square root of both sides, the square root of 6.85 is 2.617. The squares now drop off when you take the square root of the left side, and all you have is x divided by 0.50 minus x equals 2.617. Now you need to do the math. X equals 2.617, 0.50 minus x, but you don't have a quadratic here. You just multiply this out, and This is your answer. Okay, this is the term that you get when you multiply it out. You collect the x in one side and you solve for x, and you find out that x equals 0.36 molar. The other thing you need to do, and make this a habit, because it only takes a few seconds to double check that. Make sure that the answer is reasonable. Okay, what you need to remember is that we have zero point 0.5 here and our x is 0.36. So you're taking a large quantity and you're subtracting a smaller quantity. That makes sense because you're going to have mass at the end of this, or concentration at the end of this. And it's going to be basically 0.14 molar. Zero point 0.5 minus 0.36 is 0.14. Now, if this term, suppose you solve this math and you get 0.86 instead of 0.36, you know that doesn't make sense, because if you've got zero point 0.5 and you subtract 0.86, that basically tells you that you're going to have negative mass. That does not physically make sense. So double check your answer. Don't just take it at face value. Make sure it makes sense chemically. Okay. And in this particular case, 0.36 certainly makes sense. What you Where you will encounter this problem is when you have a quadratic. Remember that when you solve a quadratic formula, you always get two roots. One is going to be an impossible solution. The other one's going to be reasonable. Okay, so keep that in mind. So this problem turned out pretty easy. Okay, if you recognize it's a perfect square. Now let's take a look at the same problem, except I'm just going to vary it so that the initial concentrations are different. Here we have 0.5 molar SO2 and 1.0 molar NO2. So again, I'm going to set up my ice table. 0.5, 1.0. We don't have any SO3 uh, in the reaction so far. And again, it's still going to be the same ratio. Even though the quantities are not equal, it's still minus X, okay, for SO2, and it's still minus X for NO2. Don't put minus 2X just because 1 is twice that of 0.5. The chemistry is a 1-to-1 ratio. So for every 1 SO2, you also need 1 NO2, and you produce 1 SO3 and 1 NO. The amount here just gives you an idea of how much you have, and it's up to you to figure out uh, how much you have at the end based on that initial um, concentration. So it's still a 1-to-1 to 1-to-1 ratio, and that's always based on the balance equation. Always based on the balance equation. These things right here, there's a 1 here, there's a 1 here, there's a 1 here, there's a 1 here. And that's based on the balance equation. Okay. Now, if you set up the mass action expression for this is what you get. X times X, because that's the products, 0.50 minus X times 1 times minus X. Now that's not a perfect square anymore, because you can't take the square root of that whole quantity and make it 0.05 minus X squared. It's not. You have to solve this through the quadratic equation, quadratic formula. And that means you have to multiply this out. 0.50 minus X, 1.0 minus X. So make sure you guys remember how to do this, because even if you have a quadratic calculator or app, you still need to express it in terms of A, B, and C. AX squared plus BX plus C equals 0. You can't just take this equation as written and try and solve it using that quadratic app. You need to express it in the term of AX squared plus BX plus C equals 0. So this is what we're going to do in terms of this. Remember that minus X is X squared. This is 0.50 minus X. This is 1.0 minus X, and then 1 times 0.5, that's just 0.5. So this whole quantity is 0.5 minus 1.5x plus x squared. That's in the denominator, Okay, those are not your a, b, and c. You still need to solve that. You've got an x squared on top, so we can do that by, again, here it is. Okay, that right there is that. And you've got x squared on top. Now what you need to do is collect the terms. So I'm just going to put this over here, 6.85 times zero point 0.5, 6.85 times minus 1.5, and 6.85 times x squared. When I do that, okay, when I do that, this is what I get. Okay, that's what I get. Again, if I was in front of you, I'd go ahead and do the math in front of you, but here you can just see it. And then, of course, if you want to watch the Zoom replay, you can always do that and double check my math, double check my work. Um, when we put it in one side and then we collect the terms, we get 5.85x squared minus 10.28x plus 3.43 equals 0. It always has to equal 0. That's the term that you have. You have to have it in this form, ax squared, oops, plus bx plus c equals 0. Why? Because then we can use 5.85, negative 10.28, and 3.43. Okay, and we can put that in our quadratic app. And when we do that, okay, or we can put it in our quadratic formula if you really need to practice doing that. This is our quadratic formula. Okay, you get two solutions. And again, take a look and see whether or not which one makes sense. And what you will see is that if I've got zero point 0.5 and I subtract 1.309, that doesn't make sense because I would get a negative concentration at the end. If I got zero point 0.5 and I subtract 0.447, I get a positive concentration at the end. So this is the correct answer, okay? 0.447. All you've got to do now is stick in 0.447 in each one of these.
Professor,
Yes.
um, trying to follow along here. I didn't get 5.85 for C, and I think I missed something.
5.85 for C. Um, oh, the reason why you didn't get 5.85 for C is right here. Did you get 3.43?
No.
Um, the reason why, what some quadratic calculator asks you to put the x term as 1, okay? X term as 1, and so if you divide the whole thing by 5.85, then you get 1 for A. 10.28 divided by 5.85 is 1.757 for B, and 3.43 divided by 5.85 equals 0.586. So let me just do this again. You got 0.50 minus 1.50x plus x squared, and that's equal to 6 times 6.85. So if we do the quantity, 6.85 times zero point 0.5 is going to be, and remember that first term is x squared. So it's going to be 6.85 0.5 times, that's 3.42. So that first term is 3.42 or 3.43. This second term right here, 1.5 times 6.85 is 1.028. And then the last term is 6.85 x squared.
So we're okay, got it. Thanks.
Okay, so you take there's an x squared on top. So you subtract that from 6.85, that becomes 5.85. Okay. Yeah, this is actually 10.28. I forgot say 1.028 times 10 to the first. So that's 10.28. So our x term is 10.28. Our c term is 3.43, and our a term is 5.85. I
And
mean,
we get all these by distributing 6.85, which is our,
yeah, you have to do
okay.
that. You have to distribute that.
It would be on the other side of the equation. You wouldn't just subtract it? Because that's what I did, and that's why I got a different value for C and different values altogether. Sorry to make you cover this. I feel like everybody else gets it, and I don't.
That's all right. I totally understand. The math on these things get complicated. So don't worry about slowing me down. You need to understand how to solve these things. So just make sure I've got the right numbers here. So, okay. So what we have at the bottom, the denominator is 0.50 minus 1.5 plus x squared over x squared. Okay, let me do this. So that first term comes out to 5.85. Sorry, 3.43. So if you do this math, this is what happens. 3.43, this two, okay? These two right here is 10.28, and then this is 6.85 x squared.
I think I figured out where I screwed up.
Okay.
In the mass action expression, I kept the denominator on its own. I forgot about the x squared in the numerator. And you take the denominator, distribute it into 6.85,
Yeah,
and
you
then
do
that's
that.
equal to x squared. And since you have x squared, you can,
Yeah.
okay. That
Okay.
makes a lot more sense. Thank you so much,
Okay,
Professor.
no problem. Um,
Do you subtract x squared to get 0 on one end, or do you keep x squared?
you have to get the form ax squared plus bx plus c equals 0. You have to set it equal to 0. That's the way this equation that you see right here. Okay, let me clear this. This equation that you have right here, the a, b, and c term that you have right there, that is dependent on ax squared plus bx equals c. Uh, ax squared plus bx plus c equals 0. It has to be set equal to 0. And then you can get the a, the b, and the c term. And if you have a quadratic app, that's basically what you input into that equation. Okay. So I think someone put in the chat room, um, in the chat box, a picture of how it's done. So you might want to take a look at that if you're still. These are, hate to be the bearer of bad news, but these are problems. You need to practice quadratic formula and get yourself a good quadratic app if you want, because a lot of the things that we do are, the foundation is chemistry. So you need to know how to make sense of how to get the equation, but the home stretch is math, okay? And there's a lot of math calculations to get to the final answer. Anyway, let me try and simplify your life a little bit for certain problems, okay? And so that'll be the next part right here. Let's consider this problem right here. NOCl decomposes to NO and Cl2. So that's an easy equation. Okay. At equilibrium, so you right away you see that the equilibrium constant is small. You know it's small because that's a -5. Remember, the equilibrium constant can never be negative, but it can be very, very small. 10 to the minus 30th, 10 to the minus 60th. Those are not um, uncommon for reactions. Generally, you get like 10 to the minus 5, 10 to the minus 8. When we get to acid-base chemistry, it can certainly get very small. Um, you know it's small because it's like a thousandth, 1/1000th. Okay, if it's not the order of 10 to the minus 3, it's more like 10 to the minus 2 or 10 to the minus 1, then you got to look at the initial concentration. But that'll be more clear when we solve this particular problem. Okay, so what we have is NoCl2. It decomposes 1 mole of NoCl. So the initial starting is 1.0 mole. Okay, the reason why I put S there is because that's the starting moles. Remember that in the ice table, it's molarity. You got to express it in molarity. The volume here is 2 liters. So the initial really is 1 divided by 2.50 molar. Okay, you got to convert it to molarity. Then, of course, we have 0 and 0 that because the reaction hasn't started. The change will be, again, make sure it's balanced. It's a 1 to 1 to 1 ratio. Delta N in this particular case is 2 minus 1 or 1. If you need to convert the Kc to Kp, this is going to be, in this particular case, minus x plus x plus x. And then at equilibrium, this is 0.50 minus x. Remember, this is the starting line. So you're not using that quantity. You're only using this quantity to get the equilibrium. This is x and this is x. So the mass action expression, if you want to solve this, is x squared over 0.50 minus x equals 1.6 times 10 to the minus 5.
Excuse me, Professor, I have a question.
Sure.
Why NOCl converted into NOCl2 at the beginning of the equation?
Oh, sorry, I mislabeled this. It's not NOCl2, it's NOCl. So basically, that's a good start. Thanks for, it's basically that. So see how easy even your instructor will make. Once you change the formula, you change the balance equation, and then things gets messed up. This is actually 2 here and 2 there, which means that I need to go back to, that's why the balance equation is so important. Thanks for pointing that out. NOCl2 goes to NO plus Cl2. The balance equation is this. The initial is still 0.50 molar. This is 0, this is 0, but now your change is minus 2x. This is plus 2x, and this is x. So I hope through my goof up, you notice that the balance equation is really critical. Otherwise, you're going down the wrong path, and you probably spend 30 minutes. For some people, it might take an hour to solve. It shouldn't take that an hour to solve this problem. But basically, at the end, you've got nothing to show for it because you started with the wrong premise. Anyway, thanks for pointing that out, okay? In this particular case, what we can do now is get the equilibrium expression. This is basically 2x, this is x, and this is 0.50 minus 2x. Now, why is that important? Because again, the equation that you solve gets more complicated once your coefficient is not 1 anymore. So what we have is 2x, well, let me do this before I start on that. I want to show you the fundamentals. The mass action expression for this is NO squared, y squared, because you've got a 2 right there, times Cl2 divided by NOCl squared. And that's 1.6 times 10 to the minus 5. So right away, you can see that the math really gets hairy just because you've got a square term in there. So if you want to put this in a mathematical expression, remember that NO is 2x, so that's 2x quantity squared. There's a redundancy in the 2 there. You not only put 2x, but you also have to square it, okay? And then this term is x, and then in the bottom, it's 0.50 minus 2x, and that's squared as well. And that's equal to 1.65 times 10 to the minus 5. So to solve that problem, you would need to do this. You need to do this. You need to say, remember that that's 4x squared times x. That's 4x cubed. Now we have a cube term. And then in the bottom, we have 0.50 minus 2x squared. And if you want, you could multiply that out, but don't bother because there's a simpler way. And once you have this right here, if you have a polynomial in order of 3, then that becomes a math problem. Okay, there's probably an easier way. If it was just a mathematical, let's say that we have 4x cubed and this is a number like 38.3 equals 1.6 times 10 to the minus 5. You can solve this because x will be the cube root of what's the other side. It's not a polynomial. It's just a term with x cubed. You can solve that. That's an easy problem to solve. But in this quantity right here, you're going to have an x cubed, you're going to have an x squared, and you're going to have an x. So it's a polynomial in which you have order of 3, 2, and 1. We're not equipped to solve that. Okay, I'm not going to give you that type of problem where you have to solve it. If you just write down the equation, if you can't solve it, then I'll give you partial credit. But what we really need to do is the following. Okay, what we really need to do is look at the chemistry, because the chemistry, okay, is the way to make the problem easier to solve. But that means you have to understand how things occur. You got to understand what these numbers mean in the physical realm. So let me go ahead and do this. I'm gonna clear this right here. Okay. And the reason why I want to do this is because this is your mass action expression. Okay, this is your mass action expression right here. 4x cubed over 0.50 minus 2x equals 1.6 times 10 to the minus 5. Look at that number, 1.6 times 10 to the minus 5. Physically, that means that the reaction is not very efficient. Physically, it means that you get very little product. That's not to mean that you get zero product. It means that you get very little product. More importantly, and remember this, more importantly, if you've got an initial amount, not much of it is going to get depleted. Because if you're not going to form very much, you're not going to take away very much from the initial reaction. So what you need to do is you need to make an assumption. You can't say that x here is 0, because if x is 0, that means the reaction never starts. What you need to say is that, okay, my product is going to be defined by this x term, but in the bottom, the denominator, remember that's your reactant. 0.50 is how much we start, minus 2x. But if you've got enough initial concentration and very little amount of it is depleted, that's approximately 0.50. Not very much of it is going to get consumed. That's the key. And how do I know that? Because of this quantity right here. You make that bold assumption because you're assuming that the equilibrium constant is so small, not much of the reactant is going to be converted to product. That's not to say that the reaction doesn't go. Otherwise, you have no problem to solve. That's to say that 0.50 minus 2x equals 0.50. Guess what happens when you do that? Okay, guess what happens when you do that? When you have 4x cubed on top, and this term right here, and you get that approximation. Okay, oops. 4x cubed over 0.50. Why? Because 0.50 minus 2x is approximately equal to 0.50. Okay, you still need the square there. You still need the square there because it's still the concentration of the reactant square. But now you can solve this. You can solve this easily. What you need to do is you need to take 0.5, square that, multiply it by 1.6 times 10 to the minus 5, and that's just 4x cubed. This whole quantity, 0.5 squared, okay, is going to be equal to 0.25 times 1.6 times 10 to the minus 5 divided by 4. That's x cubed. And you can take the cube root of both sides and you can get your answer x. Okay, so we've gotten rid of the polynomial, the x squared and the x, and simplify it to a power of 3. And you can do that in your calculator. So if I take 0.25 and multiply by 1.6 to the negative 5 and divide that by 4, I get this quantity 1 times 10 to the minus 6. This quantity right here is equal to 1 times 10 to the minus 6, and that's x to the third. And if I take the cube root of that, okay, let's see, here it is. You get 1 times 10 to the minus 2. X equals 1 times 10 to the minus 2. So x is 0.01, in other words. And you see that as I work out the problem for you right here. Okay, as I work out that problem for you right there. Here it is. We make this assumption right here. And then we can solve the math. And when we solve the math, we get x equals 1 times 10 to the minus 2. So the amount of chlorine is 0.010 molar. The amount of NO is 0.020 molar. And the amount of NOCl is 0.50 minus 2x, 0.02. And that's about 0.48 molar. Now, you need to double check your assumption. Is 0.50 and 0.48 close enough to each other? It's pretty close, okay? And the way you check it is called the 5% rule. 5% rule. If the delta is more than 5% than the initial concentration, then you need to do a second iteration. If it's below 5%, your assumption was good. So what is the 5% rule in this particular case? We have 2x here, so that's 0.02, and divided by 0.50. And if we multiply that by 100, we can see that 0.02 divided by 0.5 is 4%. So it's within the 5% rule. Okay, it's within the 5% rule. And the simplifying, it's called the simplifying assumption method, is valid for this particular. Suppose it didn't follow 5%. Suppose I need a second iteration. Let me show you what you would do in the second iteration. What you would do is say that my new x value is 0.48, okay? Because in reality, you don't have 0.5. This is your assumption right here. This is where you make your assumption right there. In reality, it's not 0.5, it's 0.48, because that's how much, well, not in reality. In the first iteration, it's 0.48. So what we want to do is use that answer to do the second iteration. Remember the iteration method in algebra or calculus? That's where you get your answer and plug it back into your assumption and then get a new answer. So if we did that, 0.48 minus 2x, okay? Oh, sorry, 0.48 is the concentration here. Then we would do this. This right here would be 0.48, and this is what I would solve for if I did the second iteration, making the denominator not 0.5 but 0.48. So this is what it would look like. 4x cubed over 0.48 equals 1.6 times 10 to the minus 5. Again, you would need to solve this problem. 1.48 squared, don't forget that, times 10 to the minus 5. 0.48 squared is, let me put this in my calculator, is 0.2304, and that's over 4, and that's x cubed. So I'm going to take 0.2304 and multiply it by 1.6 to the 5 negative and divide it by 4 and take the cube root of that. And when I do that, I get an x term of 9.73 times 10 to the minus 3, or 0.0097, which is practically 0.01, okay, which was our first term. But that's how you would do a second iteration. This number right here is more precise than the previous one because you use a better starting assumption, okay? So the first answer would have been perfectly fine. I'm just showing you how to do the second iteration if it fails the 5% rule, okay? If it fails the 5% rule. So how do you validate that the 5% rule will work even before you start? Well, first of all, know that you can do a simplifying assumption if K equilibrium is small. How small? About 10 to the minus 3, definitely by 10 to the minus 4. But it actually is also important that your initial concentration is somewhat large, okay? Like, let's say we have, who's rich out there? Bezos, the owner of Amazon. He's worth billions and billions of dollars. If he gives away $100,000, then it doesn't really make that big a difference to his wealth. He'll still have billions of dollars, okay? Let's say that you have ordinary Joe out there. He makes 6 figures, okay? Let's say he makes about $500,000 a year. If he gives away $100,000, even though it's the same amount, it does make a dent. So that's why the initial starting concentration is important. If you got a big initial concentration and you're giving away, some of it goes to products, then the initial doesn't really change. But if you got a small initial concentration and you give away some of it to products, then it does make a change in terms of the equilibrium concentration. So how do we validate the simplifying assumption? Well, here it is. What you need to do is you need to look at the initial concentration and you need to compare it, because you need a large initial concentration and you need a small equilibrium constant. And this is not in your book. This is in one of the books that I've taught many years ago, but I don't know why it's not used. Remember the 5% rule? This is where it says the 5% rule is how you check. But this next page right here is how you test whether the 5% rule will apply. You take your initial reactant concentration and you divide by K equilibrium. Okay, if that quantity, if that quotient is greater than 400, it basically means that you will fall within the 5% rule. If it's less than 400, then you're going to probably need to make a second, maybe a third iteration. Okay, this right here, remember what I said, you need a very, very large initial, well, not a very large, but a significantly large initial concentration, and you need a small K equilibrium. So when you have the equilibrium in this quantity right here in the denominator, it makes that number bigger. So use this as a rule of thumb when you're doing the iteration method, methods of approximation, it's also called, okay? So let's take a look at this next problem. If you take a look at this next problem, and the question is this an iteration method or a quadratic? And right away, you can see this quantity right here, Kc is 7.3 times 10 to the minus 18. I'd do the iteration method. That's a very, very small number. If it's a very, very small number, make the math easy for yourself. do the methods of approximation. So here's how to set up this particular problem. It says hydrogen, a potential fuel, is found in abundance of water. If we can do this reaction that you see right here, and get hydrogen gas, boy, then we can run on the hydrogen economy, okay? But you can see that this reaction is not very good. It's not very efficient. The equilibrium constant, 7.3 times 10 minus 18, okay? What is the hydrogen concentration for 0.10 molar water? Even though water is a pure liquid, depending on how much you have, you can still calculate a molar concentration. That is the moles of water in the volume it occupies. And the volume could be, if this is a gas, which it is, then the volume is the container that it occupies. So you basically have steam in this container, 1 liter, and what you need to do is calculate how many moles divided by 1 liter equals 0.10 molar. Okay, if you had a liquid, all liquid water is going to have 55.5 molar. Okay, that's just the nature of it. But if you have a gas, you can make it 0.10 molar, because remember, it's the moles of that steam in the volume it occupies. Anyway, we have 0.10 molar. We don't have any hydrogen gas produced. We don't have any oxygen gas produced. But in the course of the reaction, for every 2 moles or 2 molar water that is used, you get 2 moles of hydrogen gas, 2 molar hydrogen gas, and 1 molar oxygen. So we can set up the mass action expression. And we can say that this is 2x squared times x all over 0.100 minus 2x equals 7.3 times 10 to the minus 18. Okay, you do a simplifying assumption. You say that the denominator here is approximately 0.1. You multiply this by 0.100 because that's the denominator. Now this is going to be 4x cubed. So you just solve this problem right here. Simplifying assumption. So that's basically what you see in my slide right here. Okay. And then you can solve that problem. X is just 2.6 times 10 minus 7. Again, very, very small quantity. But if you are constantly siphoning off the hydrogen and the oxygen, so you can move the equilibrium to the right, maybe you can get sufficient amount of hydrogen. And this might be a way of getting hydrogen, albeit you need very high temperatures. Okay. So the 5% rule, well, this, if you check our percentage, it's 0.0052. Definitely this particular answer is going to be a good answer to solve. And then you get away from the quadratic. Okay. Let me do another problem here. This is the reverse of the simplifying assumption, in that not much of the initial reactant is consumed. Take a look at this reaction. We have PCl5 going to PCl3 and Cl2. So that reaction, PCl5 going to PCl3 plus Cl2. And it's a 1:1:1 ratio. Okay, 1 breaks down to 2 in this particular case. Kc equals 1.8. Okay, so what you can see right here is that you can't use a simplifying assumption. That K value is not that big. It's not that small. It's 1.8. Okay, what are the concentrations of all species at equilibrium? And what is the percent reactant? So when you do this problem, you set up the ice table like that. And this term, it's pretty easy. You don't get a polynomial in the order of 3. You probably get a quadratic. And so you could probably solve this using a quadratic formula like that. And then just do the math. And if you do the math correctly, then you can solve this using a quadratic. And that's because the coefficients are somewhat simplistic. So you don't have orders of 3 and orders of 2 in this particular problem. You just put it into the quadratic equation and you get a concentration of your products of 0.0198. Okay, you start out with 0.02 and you take away 0.0198. So you can see that this reaction actually goes significantly to the right. The amount of PCl5 is 0.02 minus 0.0198, and that difference is 2 times 10 to the minus 4. That's how much reactant you have. The percent of PCl5 remains, because remember what the question is? What percent of the reactant remains? If you just stop at X, this would be an incomplete problem. You would not get credit for that second part. But the percent is just how much you have at the end, 2 times 10 to the minus 4, divided by how much you started with, 0.02 times 100. So that's 1%. This reaction goes to 99% completion because all you have is 1% reactant at the end. So that's how you do a problem like this. You need to practice it through the homework so you are comfortable, and you see many different methods of doing this. Let's take a look at this problem, and then I'll give you a homework. And if you submit that, make sure that when you submit your answers, and you guys can work in groups, your old group is fine, okay? Because we're running up into 60 minutes here, but your old group is fine. Submit one paper with your group. If you don't want to work in group, then it's fine to submit an individual paper. But let me go through this last problem right here because I want to show you the converse of the simplifying assumption method, okay? Right here we have 4 moles of SO3 is sealed in 5.0 liters. Kc is 2.43 for the reaction, and this is the reaction. It's basically the same reaction that it's basically the decomposition of SO3, okay? So in this particular case, we have 4 moles of SO3. 4 divided by 5 is 0.8 molars. We assume that there are no SO2 and O2 at the beginning. And then during the course of the reaction, this is going to be minus 2x, this is plus 2x, this is x. But look at the Kc. Kc tells you that the reaction has an order of about 9,340. It basically tells you that the reaction goes pretty much far to the right. So making this assumption, 0.5, remember that if you do the mass action expression on this, this is 2x squared times x over 0.80 minus 2x squared equals 9.34 times 10 to the 3. Well, in here somewhere, you're going to get 4x cubed, okay? I'm not going to give you that type of problem. What you need to do is recognize the shortcuts. So the shortcut here is the following. That K equilibrium constant is large. That means that the reaction essentially goes to product. That means that this value right here is probably 0.8. Sorry, this is a 2 to 1. This value right here is probably equal to 0.4. Change my color. This is 0.4. If the reaction is going to completion, then basically your starting material is going to stoichiometrically convert to product. This would be 0.8. But this quantity right here, 0.80 minus 2x, that cannot be equal to 0. Because if it's equal to 0, then the denominator in this quantity is 0, and then you can't solve it. That's where you make your assumption. Your assumption is going to be the following. It's going to be 2 times 0.8 squared times 0.4 over 0.80 minus 2x squared equals 9.34 times 10 to the third. So by losing the, by substituting 0.4 for x on the numerator, you get rid of the x cubed, okay? So let me show you how that's done. Let me clear this. That's what we get. That's what we get, okay? Here's that quantity right there. Then we're going to assume that the reaction produce stoichiometric amount of products, but we still need to solve for X in the reactant side. Okay, so this is our quantity right here. When we put 0.4 for X right here, this is our numerator. Our denominator still stays the same. Then what we need to do is we need to solve it. What we did was I took this, put it in the bottom. That's this. I multiplied this out, 4 times 0.4 cubed. That's that quantity right there. And then I kept the 0.80 minus 2x term right there. So this whole term right here is a number. Okay, that whole term right there is a number. And that is equal to 2.74 times 10 to the minus 5. And what we can do now is take the square root of both sides. Take the square root of both sides. And when we take the square root of both sides, then we get this term right here. And now we can solve for X. So we get away from the X cubed term, again, by recognizing what the value of K equilibrium means. And that's where you have to know the chemistry. When K equilibrium is small, it means not very much of the reactant produced products. When K equilibrium is large, practically means that most of the reactant converts over to product. Most, but not all. Okay, most, but not all. And so that's the assumption you make. This is basically it. We can do a simplifying assumption, and then we have our answer. So this is only in the cases where the equilibrium constant is large. It's practically stoichiometric in terms of the product, but you still need to solve for X. That's the key. Again, I'm sorry about all this math, but I told you, there's a lot of math in this problem. This is the problem that I would like you guys to solve, okay? This is, I'll read it. For those of you who are engineers in this class, especially if you're a chemical engineer, this is a typical problem. An engineer is studying the oxidation of sulfur dioxide to produce sulfur trioxide. So in this particular case, we're running that previous problem in the reverse order, okay? The Kp, notice this is Kp, is 1.7 times 10 to the 8th at 600 Kelvin. The reaction is the following. At equilibrium, so we allow it to go to equilibrium at 600 Kelvin. These are the partial pressures. Calculate PSO2. That part's easy. You just set up the mass action expression and you solve for the partial pressure of SO2. The next problem is to this system. This is now referring to this. It's at equilibrium. To this system, you add an additional 0.004 moles of SO2. So you take the equilibrium concentrations and you make the SO2 higher by 0.004 moles. Remember, I give you a volume in here somewhere, okay? Right here, a volume. So you can convert that 0.004 moles to molarity and 0.0028 moles of oxygen to the 1 liter container and raise the temperature from 600 to 1000. So initially you're at 600, you spike up those chemicals to higher concentration, then you raise the temperature to 1000, okay? The reaction reaches equilibrium and 0.002 moles of SO3 is present. So at the 1000 degrees, you have 0.002 moles of SO3 in the 1 liter container. So it's 0.002 molar, okay? What would the engineer calculate for Kc and the partial pressure of SO2 for the reaction at 1000? Does the engineer expect the reaction to be exothermic or endothermic? Okay, think about this. Turn this in before class on Wednesday if you want the extra credit. I'll go